Hey everyone, this is my video on my graph generator project, which you can go use at this URL, which will be in the description. So graph generator, what does it do? Well, it's in the name, it generates graphs. And it also gets into the area of computational geometry with the convex hull. So we can click on this black canvas to add some vertices for our graph. And we can also use this checkbox to draw some labels for it, which is just the order in which they were added. We can also left click to delete vertices, and then the labels for all the other ones will be shifted. So it's always 0 through n-1, where n is the number of nodes. So the first algorithms that we'll talk about are Kruskals and Prims, and they kind of go together because they have essentially the same purpose, which is to generate the minimum spanning tree. So a minimum spanning tree is some graph that connects all the vertices, right? So all the vertices will be in a single connected component, which means, so I'll let it play so you can see a tree formed and kind of talk about it, and then I'll explain how the algorithms are doing this. So in this tree, you can see, which is the minimum spanning tree, it's connected, which means you can travel from any vertex to any other vertex. It's all in one connected component, but it's also acyclic. There's no cycles, which is specifically what gives it its tree property. It needs to be connected and acyclic. And the way Kruskals and Prims find this is they do it in a different methodology, but they both find the minimum spanning tree. So here we're basing edge weights. They're not shown. The edge weights are not shown, but they're just based on Euclidean distance between the points. So the way, I'll clear out these vertices. Let's just start with a simple example. Kruskals, the way Kruskals finds a minimum spanning tree is by adding the shortest edges just globally. It takes all the edges, and we're working with a complete graph here implicitly. Like, we're assuming you could add any edge, like connect any two vertices. Kruskal adds the shortest edges first. So for example, 0 to 1 is shorter than any other connection between two vertices. So it adds that first. And then it looks like 0 to 3 was the next shortest. And then 1 to 2 was the next shortest. And it'll continue adding these edges unless it would form a cycle by adding that edge. For example, let's see here if we can see any. So it's adding, but then it saw there, right? It was going to try and add 3 and 0 and connect that, but it realized using its what's called a union find or disjoint set data structure, there's alternate names, that connecting 0 and 3 would cause a cycle because 0 and 3 were already in the same connected component. So that disjoint set data structure keeps track of those connected components to tell us, oh no, connecting this edge would form a cycle, and so we don't want to do that because we want a tree. So it continues on. It just skips that edge and continues on. And that's what the blue is showing. The blue edges show that it's considering adding that edge, and then because it's not white, right, the white would mean it's actually added to the minimum spanning tree, but 0, 3 never becomes white, so the edge is never actually added to the minimum spanning tree. Moving on, we can see prims. It acts slightly differently, but it will give us the same result. So Prim starts from, in my implementation, it always starts from the 0 vertex. But really, it's arbitrary what you start from. And then it essentially just builds out the tree in one piece. It'll always have one single connected component. It doesn't manage multiple like Kruskals. So it'll just add the shortest edge from a vertex inside the tree to a vertex outside the tree. So you can see it also considered all these edges, for example, 0 to 3, and then it realized it didn't want to take it because 0 and 3 are both already in the same tree, in the one tree that we have. And you can also see that a lot of the times it considers kind of the backwards edges, like it considered 3 to 2 just then. It had already added 2 to 3, but in my implementation, it also checks 3 to 2 and realizes that these edges are already in the same tree. But you can see it gives us the same result. And you could use it on a lot more complicated examples. The time complexity of prims and Kruskals are pretty good. I'll remove the number labels so you can see it a little more cleanly. The time complexities are pretty good. So it's going to be, the animation will take a while, but it's really not at all difficult to compute for just a handful of nodes. This is not that many vertices, so it's not a problem at all computationally. It's just the animation that takes a while. but we can watch it work a little bit. And so you can see with the higher number of nodes, it becomes more noticeable because you have more time to kind of pay attention, that it's just building out a single tree, right? There's no second connecting component. We just have a single tree, and it's just building that out, which we can compare to Kruskal's. I'm not going to let this finish. We can compare to Kruskal's, which builds out many connecting components. So it sees that this is the shortest edge of all edges, then this and this, and it kind of continues building out those components. So currently it just has 2 connecting components, but maybe we'll have a third. Probably not. And then eventually it'll connect these two, probably, I think with this edge maybe. Let's see, yeah. And then finally, eventually, it'll add that edge. And technically we already have our MST, but it'll continue going. We could add an optimization. Every tree has if it has n vertices, it has n minus 1 edges, just by definition. So once we add n minus 1 edges, we could just stop. But I haven't added that implementation or that optimization. So it'll just kind of keep going until it goes through every edge and finishes. I wonder what the longest edge is here. Maybe this point to this point? Not sure. I'm not going to wait to see it. So the next algorithm, which is a little bit more getting into computational geometry really, other than not necessarily graphs, is what's called the convex hull. So the convex hull, if you know what a convex shape is, it means it can't have any concavities, right? Convex versus a concave shape. So you can see this shape here, C, if it'll load, has a concavity because it kind of goes inward, right? This angle here where it goes inside the shape means it's not convex, it's concave. So a convex hull, the problem is, given these points, what is the shape? Like, how do we find the polygon that is convex and contains all of the points? And the vertices, that each vertex of the polygon is like one of the points, right? It's not larger around the points. And one way to think of it more intuitively is if these points were, let's say, darts in a dartboard, and you put like a rubber band or a string around all of them and tried to like tighten it as much as possible, what would the shape look like of that string, right? So we can look at the result. We can watch the algorithm work and look at the result to understand what a convex hull is a little bit more. And then I'll talk about how the algorithm is functioning. So you can see in this case, just to get us started a little before we get into like how it's really working, that the red, it sometimes deletes an edge. Like it'll add an edge that was white and then kind of go back on itself and realize, actually, I want to delete that edge, and it turns it red and deletes it from the white. So you can see here that these points on the inside are not included as like vertices of the polygon. They're internal. They're inside the polygon, right? If we were to include this point, for example, like go from this point to here, that would be that we would no longer have a convex polygon. That would be a concavity. So the way convex hull works is so it initially adds the most extreme point, which we're defining to be the lowest. So the lowest point is here. And then it sorts all the points around it by angle, right? And the most extreme angles, which is in this case is this point and this point, will be automatically added. Those are always going to be in the convex hull, right? So it adds those edges automatically. And then it goes around through every point based on the sorted order by angle. So that's how you can see it's kind of proceeding right to left, because this is at the next most extreme right angle, then this, and so it kind of sweeps right to left in this case, like counterclockwise. And then you can see it'll always add to the edge, until it encounters like a convexity or a concavity. Sorry. So let's look in more detail. So you can see that when it adds this edge, and then it attempts to add this edge, it looks from this vertex to this vertex to this vertex. And when it sees that angle would form a convexity, or a concavity, sorry, it backs up and and deletes this edge, right? So again, one more time. You start at this vertex, it adds that edge, but then it sees that if it were to go to the next vertex, that would be concave. So it backs up and it deletes the edge, and it continues from this vertex again. So it adds that edge and then it backs up, and now it adds an edge from this vertex to this vertex. It skips over this one and just leaves it like internal, right? So it leaves it inside the polygon. And a similar thing just happened there. It decides to skip over this vertex because going from here to here to here would be concave. So it skips over this vertex and just goes directly from here to here, from 0 to 1. And then the final algorithm that we have is actually unfortunately not animated because it's not really, it doesn't really construct it in a greedy sense like Prims or Kruskals. It's like a dynamic programming algorithm, which is, I guess, a little bit harder to animate. I couldn't figure out a way to animate it that would make sense intuitively. So I just kind of, it just shows the result essentially. So what the traveling salesperson problem is that you can see it's every vertex is included. So it goes through every vertex and it's a cycle. Like it goes around. If you were start at a vertex and go through all the other, like follow along, it's just basically a single cycle, right? There's no like branching. There's no, every vertex has only 2 edges attached to it, like, right? We don't have any like branches like in a tree. And the difficult part of it is just finding the shortest possible way to do this. So in this case, this is the correct configuration. If we were to take, if we were to instead go from 4 to 11 to 9 to 0, that would be longer, right? So it would be suboptimal. And the setup for the problem, the reason it's called traveling salesperson, is that if you imagine there are some cities that, a salesperson back when people traveled more, in person, like really, they still do, I guess, but you're trying to travel through all these cities as fast as possible. Like you're not trying to, I guess, waste gas or waste time driving and go through all these cities. And you're going to need to return to your home city eventually. And you're trying to do it as fast as possible, or I guess in as low of a distance as possible. And you have some, set of cities that you need to go through. So that's the intuition for the problem. That's the reason it's called that. But it's a pretty difficult problem. It's, I believe, NP complete or NP hard, depending on the way you phrase it, like as a decision problem or not. And so the algorithm I'm using, which is just the dynamic programming way to do it with a bit mask, is exponential time, which means, right, so there's a 2 to the n factor in the time complexity, which means that it gets pretty slow, right? So even though there's no animation, this is all just computation time, right? I press the button and we're just waiting for it to generate. So that's with 19 nodes. If we add just one more, it'll take over twice as long, or it should, based on the time complexity. It probably takes even longer, actually, like more than twice as long, because there's also, it's, I believe, n squared times 2 to the n. So adding just one more node, right, because of that 2 to the n factor, will more than double the time it takes, in theory. And you can see, I think when you get to like 21 or 22 nodes, it's going to be pretty much, impractically long. I'm not going to wait here and wait for that to finish. So I guess just don't try and run the algorithm on so many nodes because you'll have to reload the page. Oh no, you might even have to close it. Okay, well, that's that pretty much. Those are the 4 algorithms that are implemented in this project. It was a fun project. I started it just thinking about prims and Kruskals, and then later on I expanded it to convex hull, and then even later on I expanded it to the traveling salesperson. I didn't have those 2 in mind originally when I started. I have another project that I did with a team on the traveling salesperson problem, where we compared the algorithm I use here, which is an exact algorithm. It finds the exact correct solution, to an approximation algorithm that's a lot faster, right? It's in polynomial time, but it's approximately correct. So sometimes it'll find a slightly wrong solution. So that's a separate project that you can go check out called Optimal Odyssey. It's on my website. We have a YouTube channel about it on my teammates' channel. Did I say YouTube channel? YouTube video about it on my teammates' channel. And that's also another really interesting project. That was a lot of fun. So go check that out too.